Hello student. Now I am going to discuss a new chapter, torsion. It is my 12th lecture of engineering mechanics. Now come to the point, torsion. What is that? It is the angular twist of rigid body. Let's consider its object. If this end is fixed, you are applying a torque like this. Then there will be a deflection, angular deflection of the body. This angular deflection is the torsion. In case of rotating machines like generator, motor, turbine, all these rotating machine, whatever shaft is there, that is subjected to a torque, and that's why it is subjected to an angular deformation of the shaft. That is the torsion. Now, if by both the hand we are applying the same directional torque, then there is no deformation, angular deformation. But if one end is fixed, another is giving opposite directional torque, or by both hand I am applying equal and opposite directional torque, one is clockwise and another anti-clockwise, then there will be an angular deflection. Let's consider it's an example of motor rotating a shaft. Say the motor shaft is connected to a pump. Then pump is a static part, and from the motor end it is applying the torque. So the pump end resists that torque, and that's why equal and opposite torque is produces, and hence an angular deformation of the shaft introduced. And this is the torsion. Okay, now let's follow the topic with some circular shaft, as it is mostly used in rotating machines. So in our example we will explain with the help of circular shaft torsion.
So torsion means twisting of the object under the action of torque. Now here we are considering the circular shaft. The reason behind it is, in rotating machines like motor, generator, turbine, for power transmission a circular shaft is used. Then as torque is applied, so these shafts subjected to torsional force and hence twisting means torsion. Now see, just compare with the linear force and the torque. If a force is applied in the shaft here and there is no resistance to oppose this force, means under the action of this force the shaft is free to move, then there will be no deformation of the shaft. On the other hand, if an opposing force is there, equal and opposite force is there, then the shaft will deform, compress. If these two forces equal and opposite of the direction compared to this one, then it will be extension, and in this condition it is the compression. Torsion is also a deformation, but unlike here, it is not tensile or compressive. Rather, torsion is angular twist of the rigid body under the action of torque. A linear deformation means compression and elongation. It is due to the action of force, whereas torsion means twist that caused due to action of the torque. But if torque is present, means not that it will subjected to torsion. If the body, rigid body, say this circular shaft, free to rotate under the action of this torque, then this rigid body will not subject to any torsion. On the other hand, if equal and opposite torque is working, a twist, angular twist will observe there. Means then only a torsion is existing. Now let's consider this is a circular shaft and at one end it is fixed. Means if you are applying a force on the free end, equal and opposite force, this equal and opposite force will induce a torque on the shaft, and under the action of this torque, it is the shaft is not free to rotate. So what will happen? An angular twist like this. Though here it is a rectangular cross-sectional object, but in this example it is a circular shaft. So two twist will be like this. To represent the twist, it is better to give an example of the rectangular cross section. That's why I have shown here the rectangular cross sectional area twisting. A similar phenomenon we will observe here in case of circular shaft. And in that case, these let's consider before applying this torque. Torque means here force into distance. This applied force, equal and opposite force into distance between these two forces. So under the action of this torque, this line moves to this line due to torsion. Means B point shifts to B dash point. And here on the center of this cross section, it produces an angle theta. This is the angle of twist. And we are also considering overall the radius of the shaft is R, capital R. Now, for simplicity, we'll go through some assumption. What is the assumption? The assumptions are under the action of the torque, this cross section will remain unchanged, remain same. No change of shape of this cross section means it is circular, and finally after deformation also it is circular. And there will be no change of this length also. Before and after, the length will also remain constant. Means this cross section will act like a rigid body, rigid entity. There is no deformation. Only things is that it will rotate. The cross section is rotating, but not deformation. Means say initially it is the circular and finally it is elliptical after deformation. It's not like that. Initially circular with a radius capital N, and after torsion also it is a circular shape, and the radius of this that circular shape is capital R. Then what's the difference? It is moving, twisting, rotation of the circle, and hence any point on the circle B, any point on the circumference of the circle B shifts to B dash. Okay, as I have told you, the torque means the this force F into distance. Distance means the in the to find out the torque, it is force into perpendicular distance between the force. So what is the force? F and this F and perpendicular distance D. So the torque acting on this shaft is D into F. And the radius of the shaft, as I have told you, that is capital R, and at any distance we can assume that it is small r, is the, say from here to here, it is the small r, any point on the cross section it is small r, and this is angular twist. Now we have to find out what is the shear stress. You know, shear stress means force, any shear stress or any stress means force per unit area. See, in this shaft, as torque T is working, T means D into F in previous slide that I have told you, and consider any point EF, and this particular section is enlarged here. This is EF, and at any distance, consider another elementary rigid body, elementary strip, this strip, and the distance of the radius of this circle, it is circular, the circle is smaller, and along E and F there is two point C and D on this smaller cylinder, this smaller cylinder. And here, as I have told you, as this D to D dash is very small angle, so we are assuming that it is a D theta angle, as D and D dash is very close, and which is angular twist. Now, there is also an angular deformation here on this surface. This is denoted by gamma. Now we have to find out what is the torsional shear stress. Means shear stress due to application of torque. Here, this CD shifts to CD dashed after deformation. So the same figure that we have drawn again here to find out the shear stress. First consider this point, that and if this small the length of this small cylinder is dx, means here to here, this c to d, it is dx length, and cd dashed is again dx length, as the distance is very close, d and d dashed, so we can assume that both the length is same, and the angle formed here is gamma. So this angle can be termed as, we know that AC cos to R theta for any angle circular deflection, AC cos to R theta. So similarly, this DD dashed equals to this is this length into this angle, means dx into gamma, or gamma equals to DD dashed by dx. This gamma is called the strain, means deformation per unit length. This length, this again length, means for dx length the deformation is dd dash. So this is the strain. Now again, for this circle, this is equals to r, this is equals to dd dash, and this is d theta. So we also can write down dd dash equals to r into d theta, the arc length, similar to this equation. So again, dd dash equals to r d theta. And from this equation, This dt dash is again gamma into dx. Now, from this equation, we can write down gamma equals to r d theta dx. Now we have to find out what the shear stress as force is working there. So stress is also working. And what is stress? Stress means the force per unit length. The force that causes this strain, shear strain. The corresponding stress is called the shear stress. So let's consider any segment, very small segment like this. This is CD, this is another point, it is D dashed, and this is strip. Then what is the shear stress? Shear stress is working along this surface. Now we have to find out the magnitude of the shear stress. Okay, and now to find out the shear stress, so let's go through the equation. We know that it is the counterpart of the Hooke's law. From the Hooke's law, we know that shear stress and shear force, shear stress and shear strain is proportional, or stress proportional to strain. So here shear stress is proportional to shear strain, and this proportionality constant is called modulus of rigidity G. So G equals to tau by gamma. This tau is the shear stress. So from here we can write down tau equals to gamma into G, and substituting the value of this gamma from the equation, previous equation 1, gamma equals to r d theta dx. As we need to mention here that in the last equation we have proved that the gamma equals to r d theta dx. So finally tau equals to this. It indicates that the shear stress is a linear function of r radius. When r equals to 0, means at the center, shear stress is 0. So as it is linear function, so we can show this shear stress value like this. The red line indicates the shear stress. And the magnitude is from here to here, it is maximum. At this circumference, it is the maximum shear stress. Now, what is the torque that acting on the body? Now let's consider on this surface any point with area dA. The force perpendicular to the radius is equals to dP. So dP means what? Shear stress into dA. We know stress means force per unit area, or force equals to shear stress into area. As this area is dA, so dP equals to tau d. Now write down the shear force tau dA. Substitute the value of shear force here and simplify, and we are getting the force equals to this. Then what is the torque? We know torque equals to the force into distance. Now as we have assumed that there is no deformation of the circle, rather there is a rotation, and this rotation is caused due to the application of torque. This rotation is caused due to the application of torque. So what is the torque? Torque is the force into perpendicular distance from axis of rotation. Here this is the axis of rotation, means parallel perpendicular to the cross section area, this area. Means the axis of the shaft, along the axis of the shaft. About the axis of the shaft, the area is rotating. Now dP, as you have calculated here, this, and the torque This for a small area, the torque is dt equals to rdp, distance into force. Substitute the value of dp from here, and we are getting this equation. Then this torque is a function of radius, and for this elementary section d theta by dx, we can write down like this. Then the torque equals to d theta by dx g into integration of 0 to a. Just integrate it 0 to a. Then 0 to a r square dA. The integration 0 to a r square dA, we know this is called the polar moment of inertia. As I have told you, this is equals to polar moment of inertia that we have discussed in kinetics of rigid body, this equation. So substitute the value of this 0 to a rho square dA equals to j. We are having the torque equals to this d theta by dx g into j, or d theta equals to this. And we know that the limit of this dx is varies from 0 to L. Total length of the strip is L. So hence the total angular twist of the entire length equals to T. Integration of this is equals to L, TL by Gj. This is very important equation to find out the angle of twist. And this equation is similar to the linear deformation, means in case of compression or extension, that I have told you at the starting of this lecture, that under the action of tensile or compressive force, the uh, rigid body deforms, means compressed or elongates. And in that case, the elongation del equals to PL by EI. P is the applied force, L is the total length, E equals to modulus of elasticity, and I equals to moment of inertia. And here this is equals to TL by Jg. This is similar. In case of a linear force, it is the linear deformation. In case of the torque, it is the angular deformation. And the equivalent deformation formula is this. Here, our concern is this equation 4. Then combine equation 1 and 3. We can write down this d theta by dx gamma by r equals to t by g, or gamma g equals to tr by g. Then just substitute gamma g equals to tau, and we are getting tau equals to tr by g. Means the shear stress produced equals to torque into radius divided by polar moment of inertia. And this shear stress, as it is a function of distance, so the maximum value, it will be for maximum value of R, which is equals to capital R. So maximum shear stress developed on the circumference, and the magnitude is T R by J. So from here we can write down the T by J equals to tau max by R, G theta by L. Now it is the torsional moment of resistance, or resisting torque. Actually, whatever torque equation we have derived, it is not the applied torque. Rather, if you apply a torque, how much torque a shaft can withstand without failure, that idea we can have from this torque equation. And that depends definitely, that is depends on the polar moment of inertia. And for a circular shaft, we have derived the equation. For circular shaft, the polar moment of inertia is this, and for a hollow circular shaft, this is the polar moment of inertia. And then as it is the resisting torque, so torque divided by the applied torque divided by angle of twist, this is termed as the torsional stiffness, that is equal to jg by L. So this is all about our these lectures, and we have completed. And now this is the references that I have used to complete the lecture, to prepare this lecture.
Okay, so this is about the torsion. We have derived the equation of angular deformation theta here in terms of the diameter of the circular shaft, the modulus of rigidity, and all other parameters, and also use the polar moment of inertia of the circular shaft. So thank you for listening this lecture. And in the next lecture, means in the 13th lecture, I will discuss some numerical problems. We'll try to solve numerical problems based on this torsion. Thank you for your patience and attending in the classes. Thank you.